Got a great panel here today. My name is Dan Milroy. I'm from the Lawrence Livermore National Laboratory. And I have with me today Evan Bollig from AWS, Greg Nawrocki from the University of Chicago, Tom Scogland from Lawrence Livermore National Laboratory, and Vanessa Sochat from LLNL as well. So I want you to note that we've got a QR code in the upper right hand there. So I'm going to be taking questions from the audience if you prefer to submit via browser. And we also have some poll questions for you too, related to the theme of this presentation. So the background behind this basically is that we have some US initiatives such as the Genesis mission, the Lawrence Livermore National Laboratory Future Generation HPC Center, the American Science Cloud, et cetera, that are kind of paving the way for distributed workflows. So think geographically distributed workflows. And the theme of this particular panel is what kind of infrastructure and technologies are required to support these workflows and kind of descriptions of the necessities of the workflows themselves. So without further ado, I want to get started. What I want to do is give the panelists maybe 3 or 4 minutes to go through and answer a few questions, kind of give a little bit of background on themselves, and also answer these 3 questions. First, do you think distributed scientific workflows are actually aspirational? So do they actually exist? Or are there important motivating examples or existing examples? Second is, what's driving the demand for workflows to run across geographical areas? And third, of course, how does your work support or enable distributed workflows? So I guess in alphabetical order, why don't we start out with Evan?
Great, thanks. All right, so Evan Bollig, AWS. I'm a high-performance computing solutions architect. So I help customers move to the cloud and architect their environments to do both high-performance computing and distributed computing across the different regions that we offer. From my perspective, science does exist in a distributed fashion already. So we have 39 plus regions around the globe. We have different pools of capacity in those regions. Each region is 3 availability zones or more. We've got local zones as an option that move the data centers or the availability zones closer to our customer sites. When we talk about science on the cloud, you pick a place that it lands, a region or an availability zone. You use services that are available there, and you spin up your compute, do your research, whatever you need. Sometimes capacity varies, right? Like if you have GPUs in one zone and you have high-end CPUs in another zone, you have to think about how you're going to move the workload from one to another. And we have customers that do that every day. And it's a standard pattern now that we architect the environment to help you move the workloads through. The challenges that we see is that having a compute somewhere is part of the problem, but really you got to get the data to it. So it becomes a data distribution problem. And we also architect our services to move data across high availability and across multiple AZs and distribute that so that it can match up with the compute. I forget the rest of the questions already, but are we there yet? No. There's still always more work to do.
Yeah, I think that's great, thank you. So Greg, how about you?
Yeah, sure. So I'm Greg Nawrocki. I'm the Director of Subscriber Engagement, I guess, is my title. I'm at the University of Chicago. I'm with the Globus department. We are actually a department within the University of Chicago. If you're not familiar with Globus, it is a platform for distributed research. We do data transfer, data sharing and collaboration, remote compute, distributed compute, and all kind of tied together. We've got a nice automation platform that kind of ties everything together. So distributed workflows are a real thing because we are doing them. Some examples, just here at Argonne National Laboratory, most of the beamlines use Globus to move data and do their workflows. We've got several workflows where data's moved to the ALCF within Argonne and some compute's done and sent back. So we've got lots of kind of large-scale examples, smaller examples. You see a lot of the biological scientists now with their instrumentation and using Globus and Globus workflows. to move things around. So yeah, so it's a very real thing. As far as the reason for the distributed geography is really, I think, collaboration and just different people in different locations needing to get the data, and as Evan said, also resources, getting them to the right resources. But there's also kind of there's the physical geography, which I think is shrinking. You've got people like ESNet that with the networks. Sometimes it's easier to move data halfway around the world than it is to move it down the hall. And there's the physical geography, which I think is shrinking, but there's kind of the virtual geography of the user space as well. You've got biological scientists that were not traditionally high performance computing people needing it, social scientists, so you've got that, as well as kind of pushing the distribution and the need for workflows to the edges. Right, you've got to get data now off these instruments and then up to where you need to process it. So it's kind of moving it that way, as well as the other side. You've got publication mandates, right? You've got data sharing agreements that you need to put into place. When you publish a paper, you can't just publish the paper anymore. You have to publish the data. So it's kind of moving those workflows to the edges there. So sorry, I kind of turned that a little bit on its head as far as geography goes.
That's fine, no problem. Thank you for the answer. Tom, how about you?
All right, so I'm Tom Scogland, as Dan mentioned. I'm at Lawrence Livermore National Lab. I'm the lead for the Flux project, or resource manager, and do a lot of heterogeneous computing. So when we talk about distributed computing in my world with the national labs, we tend not to do a lot of geographically distributed computing in the classic sense, like with Globus, because of various things. But by agreement and by necessity, we actually have a lot of science, including production science, that happens across the tri-labs. And I have various vivid memories of people coming back and saying, all right, I got some great work done. How do I get my 10 petabytes back from Lannel? No.
With a truck.
And this is, so we have a lot of distribution and where our compute happens just because of the way that some of these agreements are made, but there's very little by way of infrastructure. Like ESNet actually is an excellent example of an attempt to fix this, but there are parts of the system that are still literally somebody ships a drive from one site to another, or carries one down the hall, in fact, as you were pointing out, Greg, because that is all that's set up for it. So there's definitely a need to build out more of this, make it more accessible. And I think that's where a lot of the challenge is, because we have these kind of exception proves the rule things where there are people that use Globus, people that use, to my surprise, I recently found out Grid Engine is serving a similar function in some parts of the world with some success. But the vast majority of, at least our scientists, are still in a more localized single machine or single cluster or single site kind of setup, and don't have a good way even to collaboratively share data from site to site, like at all. So it's an ongoing challenge, and there's a real desire for it, but a kind of a chicken and egg problem, at least for us, where the workflow currently doesn't exist that does this. So proving to the people who would pay for it that we should build it is a recurring problem.
Alrighty, that leaves me, last but not least, actually maybe least. I'm Vanessa Sochat. I'm a principal computer scientist at Lawrence Livermore National Laboratory. I come from a background of imaging analysis and then container technologies. Now I work in converged computing. So lots of Kubernetes and cloud, lots of Flux framework. So let's see, distributed workflows. I think this is a little bit of like a field of dreams sort of thing. Like if we build it, it maybe will run. I think the answer is yes, no, although I have a healthy amount of skepticism. So first, I was actually thinking of that exact workflow with ESNet and LINAC. and how that was driven by collaboration. So I do think there are these strong use cases where you have an agreement between institutions and they have a need to move that data, usually because of hardware or machines that for example, one lab has that another lab doesn't have, and so that makes no sense. My skepticism comes from many places. So the first is that I kind of see these, big national labs or institutions that have this specialized equipment or hardware, or maybe we have like 5 GPUs, and can't compete with the cloud there. But I don't get the sense that we like to share. I don't get the sense that we're going to say, oh yes, we will open this up for other people that do not have access to these resources. And so especially with resource contention, I only see that this might happen through sort of an accredited collaboration. So that's one point of skepticism. My other point is the fact that this entire compute ecosystem is changing so rapidly. And I'm not even convinced that national labs and kind of the traditional folks that have been doing science for as long as they're going to doing it are going to be oriented or even be able to accomplish that as we move into the future, because we see all of this money that is pouring into AI ML, which understandably, I guess for the cloud, and actually I'm really glad Evan's on the panel because I have lots of questions. Money is pouring into cloud for this, but on the other hand, it means that less money is possibly going into the Office of Science, as we've seen, but it also means that the things that get awarded at labs that are currently trendy now have to do with AI ML. So we're taking a very strong stance about what we think the future looks like, and the question becomes, does that future align with getting sort of answering more traditional scientific questions? I don't know the answer to that. Now, in terms of the other questions, what are sort of some issues that are going to come up? So as usual, I think there's a bigger problem with people than technology. I think, if we figure out how to move the data, maybe we'll move a smaller piece of the data. I think the bigger issues are going to come down to policy, security, even if we can, like whether we'll be able to or allowed to. Just for me to access like GitLab, like often I cannot access the things that I need to access. And so the idea that, you're just gonna automatically with agents get access to some data that's on a totally different place, I am very skeptical of this. I could go on, but I think I'll stop for now and save the rest for the panel.
Sounds good. All right, so I'm going to move into some preset questions, but I also want to encourage the audience to pose questions too. Please raise your hand. Please, again, scan the QR code and enter your questions online, fill out the polling, etc. We want to make this as interactive as possible. I'll be disappointed if I make it through all my prepared questions. So try to stir up some controversy. You want to hear some interesting opinions. So I guess my first question is, so cloud hyperscalers currently deploy planet-scale distributed services. Do clouds actually solve all the distributed workflow problems? Leaving this one open.
Do they, Evan? Tell me.
Okay, this is my personal opinion. Sorry. No, we don't. And we're always improving. And the key thing to remember is that we're a business that builds in response to customer voice. So we hear your issues and we go and action on those. So when you find a pain point, when you find we're short on something, tell us, and we can action on that. I mentioned capacity pools varying across the globe. That's one way. It doesn't make a ton of business sense to deploy the exact same hardware across the entire globe and have the exact same footprint for all of our customers. You have different needs. So we want to address what your needs are. Also, carrying a ton of excess capacity doesn't make a ton of business sense. I mean, if the labs carried multiple top 500 systems in spare, in reserve, what would the bill look like, right? So we have to think about how we can handle those types of input demands and meet your needs. And we do a ton of forecasting to try and stay ahead of the demand curves. As far as services go, you'll see that our services can vary across the different regions as well. We have, just here in the US, we've got the commercial regions which have a ton of service bells and whistles. And then you look at GovCloud, which is intended for government workloads and export controlled workloads that need to stay in the US. And the service feature list is pared down because we have to go and clear all those additional functionalities before they can move up to the other region. So no, I don't think we've gotten there yet. And I think that in terms of the impact it has on science, you do see a lot more of the research projects that are shifting from one region or another, or they're so I'm even guilty of this. Before I joined AWS, we didn't have the equivalent of AWS Batch in GovCloud. So I published a paper on how do you build the equivalent of AWS Batch using Lambda functions, right? So you bubblegum and duct tape your way to a solution, and it works. And then you go and convince the company to land the service that makes it managed and streamlined and fully supported in that region, and that's what you see in the full portfolio now.
Does it remain bubblegum and duct tape, or does it
No.
Sometimes.
Sometimes.
How often does a prototype become a product in that process?
Yeah, in that particular case, just the proof point that there was a serious customer need for a cloud-native scheduler or a container scheduler was enough for the teams that were already working on that within AWS to go and look at how do they harden the service they were developing and then move that over to the region to be available. None of my code, to my knowledge, ended up in AWS Batch. But we were on the similar parallel thought process, or parallel talk tracks for what it should be capable of doing.
I'm going to piggyback off of something that you said. I actually want to start with a win. So it is very true. I think we need to acknowledge that what cloud and industry does is driven by the customer demand. So again, back to AI ML, and that makes sense. The win in that space is the invention of batch in Kubernetes. So that came as a result of needing AI ML workloads, but it was the first time that they increased the abstraction of something running in Kubernetes that was not a service. It would start, it would complete, and that was very analogous to HPC jobs. So all of a sudden we have a unit of operation, at least in Kubernetes, that maps better to a step in an HPC workflow. So now to get back to the initial question, how do we kind of connect these dependencies? I think the best thing I like to do is to kind of think of traditional HPC, let's say I'm running something there, as compared to cloud. So what are the differences? Well, when I'm running on traditional HPC, I have a queue. I put my workload units in the queue, maybe I'm using SnakeMake or Nextflow or what have you, and I get kind of an estimated time of starting. When I do something in the cloud, at best I have like a probability. Maybe I get a spot score if I'm using Spot. If it's on demand, maybe I'm gonna wait for 35 minutes and then it's gonna kick off and tell me that they're out of stock or quota. And so there's no guarantee on that. And so that's the first big feature I think that I'd really like to see in cloud, is this ability to actually make a reservation where you get a guarantee on a time to start on something.
Yeah, so actually I was going to go off something similar. I mean, I'd love to be able to give a time to start, even in HPC, to be honest, but the best we can do is it might start at about this time. It will eventually run, I think is what we try for, right? But the thing that actually we've heard a couple of times is, there's a different availability in regions. There's different availability in clusters and HPC centers. And I think we have a similar gap in both places where, well, it's a little bit exacerbated in cloud actually by the fact that you don't get that guarantee that something will eventually run. It may just get kicked back at you. But when you go for capacity chasing, you want to find some place where you can get a resource. I have yet to see anybody that actually enables that. Like, you can do it, but it is something you have to manually manage. There's no way to say, I want this to run somewhere. Do it, unless you set up something like a Globus or a Grid Engine or a Moab type solution or something. And that means that while, yes, there is an option for distributed computing, it is, well, in a scientific context, often go poke the grad student driven rather than actually service enabled, right? And that's something I think we collectively need to work on.
Tom, do you think we'll eventually be running stuff on the moon in space? I mean, that's where a lot of clouds think we're going.
I have gotten questions like that where actually somebody, when I worked on the Green 500 list, somebody wanted to know how we would score a supercomputer built out of a swarm of low Earth orbit satellites powered by solar panels. because technically it would have no input power. I'm sure we'll end up with some amount of compute happening that way, but not soon.
And I'll take it in a little bit different direction again, because we run our Globus services in AWS, so it's very important to us. So as a kind of a foundation for distributed workflow services, I think it's very important. And also, as mentioned, for bursty things, right? When people need things, we've developed Globus to be very agnostic as far as storage goes. S3 is one of our connectors. People connect to that all the time. So being able to move between different things, I think, is really important as well.
Yeah,
and cloud provides that.
Actually, when you talk about services, I think that's the most impactful change that we made in our community. You go back a couple decades, and we put a ton of effort into service-oriented architectures and having defined APIs to communicate, and that allowed us to move faster and to scale and to provide qualified services that would serve the batch scheduling, to do data movement, to even wire up the instances that you would see on cloud. Being able to define the unit of what your compute is, your storage, your networking, and everything, and be able to stitch it into the experience that you want in terms of infrastructure. And we have seen an explosion in different architectures that folks come up with.
Yeah. And you mentioned with GovCloud too, and the services that are running there. What we're looking at, we did a FedRAMP gap analysis. What can we do to be FedRAMP certified? And some of the things we need in FedRAMP, some of the services that are running in AWS aren't quite there yet, in GovCloud rather. So so hopefully we're
working on it.
Yeah, yes, you are.
All right, so Brian Vanessa from Livermore. I spoke yesterday morning. Thank you, guys. So you guys have talked a little bit about sort of cloudy capabilities, and that's good, but that I don't think really gets at the heart of the problem. And so Tom mentioned something that kind of gets at it, which is what really drives, in my opinion, distributed workflows is unique assets. The reason the Tri-Labs have an issue about moving data around by FedEx or whatever is because there are leadership class systems that are deployed in a cycle between Livermore and Los Alamos in particular. We have Argonne and Oak Ridge, which have leadership systems. So then you sit there and say you have terabytes or petabytes of data, and it's often more practical to move to where the data is. But you guys haven't talked about laboratories and experiments and sort of unique, unique assets. So National Ignition Facility, you think outside the US, CERN, these kinds of things where, Vera Rubin Telescope, when you're generating massive amounts of data and it's impossible to move the entire data set to where your compute is, that's what's driving a lot of our needs for distributed science. So I want to hear your thoughts on that.
Agree?
Well, and so from the Globus standpoint, right, we've always been the data transfer guys, but we recently developed Globus Compute, right? How can we move compute a little bit closer to the data? How can we move those types of resources and distribute those? So we've seen that problem as well, and we're working towards solving it.
Yeah, I think there's no one-size-fits-all solution, unfortunately. I mean, it would be great if we could just say, well, we'll make the pipes bigger, but then people make the data bigger, and then the problem perpetuates, right? There's a reason we still have SneakerNet, unfortunately. But I think we're getting to a point where the more we can leverage different sources of compute, where we'll have more options for finding compute near where we need it. I had an interesting conversation with the folks at Pawsey about this, about why they built the supercomputer where it is, right? And if you're serving the square kilometer array, it kind of has to be there because you can only get the data so far before you have to process it to make it smaller. To some extent, we need that flexibility so that we can get compute close enough to be able to handle the amount of data that we need. And that means we need to have both a way to get kind of the authentication authorization for some of these things.
Yeah,
And-
Tom. Sorry.
Well, no, and to be able to leverage resources that people have built close enough. Some of that'll be ours. Maybe some of it will be, edge compute from cloud.
Right,
I don't know.
and policy issues, like you said, can drive that because maybe you can't move the data, right? You can't move it to somewhere else, so you need to bring compute to it.
Yeah, and Tom, I agree. If you only have one place where you can process your data, that actually is also a single point of failure. And I want to actually share something that Andy Howard shared with me yesterday. Is Andy here? Anyway, shout out to Microsoft, because this is from Andy. But the question is, like, do you have to actually move all of the data? Because maybe for a particular processing set, you can move a smaller subset of data, and then all of a sudden it does come more feasible to move it to something that's a little bit further away.
So when I hear this commentary, so one thing that stands out in my mind that I always try to voice to the community is that we're lucky where we're at today. We have the ability to communicate, we have the ability to share. Whether we do so or not, is up in question. But HPC has always been super specialized instrumentation. It's not just compute. It's not just a server sitting under your desk, right? It's a highly tuned, specialized piece of equipment that you look at the same way you would the square kilometer array, the same way you would for any major acquisition for instrumentation in a lab, right? And the fact that we have the ability to send work to be done on that instrumentation, get results, like that is incredibly powerful. And if we're not taking advantage of that, it's because of rules around how you access or who can access or what type of data can access, and those are really policy decisions.
So I want to dovetail in with that and kind of interface with an audience question, and that is, what is kind of the distribution between the distributed computing, as it were? How much of it is a problem of data management versus how much of it is a problem with compute allocation and management? Is it 50-50, 25-75? Are they the same problem?
I think it depends,
Yeah.
right? I mean,
It's a fair-
right, and maybe it even depends on the domain, right? For high energy physics, it's probably different than it is for life sciences. I need to think about that a little more.
Okay.
Yeah, I think I'd say it depends on where you scope it, because we have different versions of this problem. As Dan very well knows, we've been working recently on trying to solve the distributed problem even in a in-site context. You may have common storage that's easily accessible, but have a serious problem being able to actually distribute your workload across siloed clusters. Or you may be in a situation where you have non-cross-accessible storage, but you have a single federated scheduler, like some of the sites in Europe have. And then when you go another step out, as soon as you start considering something that has one more of those problems, it shifts where that part of the problem is. I mean, when you start talking about widely geographically distributed, I think the more insoluble problem to some extent. I mean, the speed of light is what it is. Moving data is going to take some amount of time no matter what we do to it. We can make the bandwidth higher, but just moving the light that far or the electricity or whatever has some immutable amount of time behind it, right? So there may be a point where we can solve the problem of selecting resources. We have not done that yet. That is a very important thing that we need to do, but I think the long-term issue is any large amount of data that has to move.
So we can't speed up the speed of light? That's an option, I guess.
No one knows yet.
I don't know a way.
All right.
Let's go with that. I guess unless we can, well, I suppose we could stop moving it through materials and move it through a vacuum, but that only gets us so far.
Dan, can I ask Evan a question?
Please, yeah.
Okay, so we have all these initiatives coming out, Genesis sort of initiatives coming out of the lab, and we're basically kind of announcing that, okay, we're going to make entire centers that are more cloud-like. So are the cloud vendors kind of looking at us like, oh, children, we started this thinking process over a decade ago. And so are we essentially like just starting with kind of to tackle the same problems that cloud started thinking about a long time ago? And you're just kind of entertaining us?
No. Okay, so there is a dimension of we've been down that path, and we can teach you, or we can show you where the pain points lie, and we can help move you faster. If you go out and you try to build the equivalent of AWS in terms of service capability, it would take you about a decade to catch up because there's so much in terms. So we have this really broad portfolio of capabilities, and it would take a long time to develop each one. It's not oh child situation. It's more like, you know, we understand why, because we've already proven that there's a ton of value and merit to going this direction. We often, though, and you hear from me on this directly, I question why you want to focus on one thing versus another, because I think that if you reuse a lot from the community, you wouldn't have to walk the same path. You could leapfrog. Yeah. And in any way that we can, we want to help you move past and then show us something new so we can continue to try and leapfrog, right? Like it's not a negative view that we have of what you're doing.
So that's a good question. With respect to that span of capabilities, what things should we be focusing on, or what problems haven't you solved, so that if a research team worked on them and came up with a solution, you would think that is a valuable contribution?
Yeah, again, so this is my personal view, because there are so many other experts that are looking at this as well. The number one service in any cloud offering, it doesn't have to be a cloud provider. It could be you build out OpenStack, or you build out OpenShift or some other solution. You're going to find that there's an identity and access management. There's some sort of access control. There's some sort of governance around how you access services, which actions you can take, who can take those actions, and how you delegate. You have to solve that first, because that's your policy challenge, right? That's where you answer that question of who can actually touch those special instruments. And then you move on to, all right, well, assume that to be true. Now we figure out what other service capabilities we're offering. And the way that the providers have all built out, they start with the core storage, accessing the data, sharing it out, then the compute. Then once you've got those two, you can start looking at how do you improve the networking, how do you improve more managed services on top of that, because you can build out some really interesting file sharing, enclave type approaches, and so just grow a little more organically that way. I think you can reuse a lot of the compute and storage definitions from the public sphere, but you can't. I don't see a direct path to just reuse identity and access management in the labs, for example. I think you have to solve that.
How do you see like federated identities, like in common, playing into that? Are they going to play an ever-increasing important part in that?
I think so. In the past, I've worked with team at NASA on an open science portal, an open science initiative, and we were looking at federated identities that would give the public access to do open science. Their mentality on it was, look, if you have data that's open, it means nothing until somebody can actually get access to it and analyze it and come and answer the questions that are pressing, right? And so citizen scientists need a sort of public federated identity. They need some way of bringing their credential in. And I think that's going to play an increasing role in Science Cloud and other initiatives.
Interesting. Yeah. I mean, it's not like we don't have that, right? I mean, we have some things that resemble this. Like OneID is one, right? It ties together all the different authentication methods and identifies a person who's been like background checked under DOE. That's on the open side. And then, I mean, we have ESN Hub on the classified side. So there are at least some federated identity systems, and the OAuth flows for OneID work pretty well. So we wouldn't be starting from scratch, right? Like we do know who some of these people are. I think the tougher part at least for a lot of like DOE people, is associating external people with accounts, especially if we want to do it quickly. Because right now, like getting it into one ID requires us to do all the stuff that we do to get you accounts on like supercomputers. We'd have to come up with some, I don't know, lower security tier for one ID, which is possible. But I don't think we'd be starting from scratch. We do have systems to do this.
Yeah, I will say, and this is, slightly showing some of the dirty laundry, right? But we could have that extra level, right? We could have a more open identity. But the problem is once you get inside any lab network, especially any lab compute network, a lot of the services have that classic Unix identity mentality where if you are on the network and you have a UID, you are authenticated, you have basic rights on things, right? So if we wanted to add an extra level like that, there are a lot of services that need mechanisms to be able to tolerate the existence of that extra level to allow access to any given site, right? So we have a lot of the base infrastructure, but there's a lot of software that needs updates to be able to manage that.
Right, how do you map to those local resources?
But there's a fundamental disconnect here, which is cloud providers like AWS are pay to play. You bring a credit card, you can get whatever compute cycles you can afford out of your pocket. FFRDCs, we are full cost recovery national assets where we are, all of our resources are purchased through congressional appropriations. All of our cycles are allocated to either mission or to science programs that are vetted through peer review, things like insight proposals. And so we can't just allow a random citizen scientist to come and say, cool, like Vera Rubin dropped some new data, let me go grab all of LCAP and try and process this. There's a process. And so we really need to think about, as we grow Genesis Mission, how do we balance, these two different ecosystems where on the federal side or the contractor side to the US government, we have a different approach to how we manage this and how we can allocate our resources to be good stewards of the government dollar.
Yeah, and that's absolutely true, right? This is, whatever solution comes out of this, it can't just be anybody who has an identity can get any resource, right? There has to be some mapping for what that user actually has access to. And that makes some of the problems, especially in actually resource selection, I think Dan mentioned that earlier, much more interesting because it means different requests will have different options of availability. But yeah, it's a tricky problem.
Yeah, and the same is true in academia,
Yeah.
right? Just maybe not to the extent.
Right. Does Todd still have a point?
What does Globus do? How does Globus do that?
How do we do?
Yeah, identity management.
Oh, so we use federated identities.
Oh, okay.
Yeah, and Globus uses federated identities. Yeah, as well as Google identities, GitHub, and let's see what else, and ORCIDs as well. Yeah, so you can use all of that to log into Globus. Yeah.
All right, I want to switch gears a little bit and ask one of my prepared questions, and that is, are AI agents the final form of the workflow manager?
Workflow manager.
So I have some opinions on this. I guess lots of people have opinions. So when I think of an AI agent, and I compare it to a state machine, and with the state machine, the AI agent, the possible steps are basically the tools or the functions that are provided by the server. And instead of a deterministic model, which may be more true of a DAG that doesn't have cycles, with a state machine it becomes probabilistic, right? Because maybe your workflow step is going to fail and the agent's going to say, oh no, let me try again because I'll just keep going. So I think in some respect, using an agent is more like using a probabilistic state machine. And what we have to do is add guardrails, so maximum number of attempts to make sure that it doesn't kind of go off into the weeds with respect to execution. I do think it's a positive movement in the sense that it's really interesting if you look for different workflow. So probably folks are familiar with Paolo Tomaso's GitHub repository, awesome workflows. The number of workflow managers in HPC is astronomical. Now, to be fair, there are kind of a few predominant ones, but it kind of seems like the case that everyone's like, oh, there isn't the perfect workflow manager for me, so I'm going to make yet another workflow manager. So we definitely have too many workflow managers, but the most interesting observation I'll make is that most of these are DAG-oriented. And so the thing I'm most excited about agents and why, thinking of an agent as a state machine as the next kind of workflow tool is the fact that it is not traditional DAG-oriented, because you can have these cycles. So I think I'm erring on the side of yes. I do think that the landscape is going to change. So MCP servers right now, in the way that they're designed, there are quite a few limitations. I won't go into the details here, but I think as the infrastructure change, as the MCP standard changes, we're going to obviously see changes to the agents that use it, and it's a pretty exciting direction and a great time to be alive. Okay, I'll stop talking.
Yeah, your observation about state machines is interesting. We use AWS step functions in Globus flows as our state machine. And where I see AI agents kind of playing into that is really kind of being able to better determine an input schema, right? All workflows are run differently, and different people may run them differently. And sometimes it takes a lot of effort to tee that up and get that workflow running. I think AI agents can certainly help with that and get that kicked off. The other thing where I think they play into is with non-structured data, like just kind of open schema metadata, because we've talked a lot about the large data and being able to parse that out. Being able to parse it out based on metadata, I think, is going to be important, and I think AI agents are going to play into that, teeing up the metadata as well.
Yeah, so to kind of build on that, I guess my direct answer to the initial question is no. They're not going to be the final workflow managers, because it's not really what they are. You could use one in a cyclic manner, like Vanessa's talking about, and then you can build something up. But at the end of the day, I think that the thing that they're giving us potentially, at least right now, is a way to generate potentially a new workflow that then you would want to run on something that can execute those, right? Or you lose something of what you get from a traditional workflow manager in terms of you won't be able to queue things up or chain them together as efficiently as you would otherwise. So I think there's still, at least for now, something of a split there where you may transition back and forth between a traditional workflow manager and especially on failure or something else where you may need a cycle or a change back to an agent.
But if the agent so the agent can make a decision though. You can ask an agent not just to give you back some kind of asset, but you can ask it to give you back a structured response with an explicit decision. So how is that so different from a deterministic decision where you've hard-coded a workflow design in a YAML file?
Right. Well, it isn't necessarily. Like I said, you can use it that way, but
you don't think it's going to replace it entirely?
Right, because that would mean that you have to go back to the agent every time you get a response. You can't queue up a fan out or do other things.
Well, you could just have a step that actually goes to a more traditional kind of workflow manager.
That's exactly what I was saying, yes.
One of the huge strengths, I think, so for folks that have worked with traditional workflow tools, one of the most annoying things ever is actually just making sure the inputs and the outputs of different steps match up. Yeah. I mean, it is really hard. Yeah. But with LLMs and with actually MCP, if you annotate your function, so I mean in Python, like from typing import annotation, if you annotate the inputs, if you annotate the outputs, if you write a doc string, the agents are so good at coming up with that input and that output in a dictionary, for example. Now, where you run into trouble is actually with the state. Because as you're running something and you have kind of some memory in an agent, or maybe you're not keeping memory, what happens when something goes wrong and you need to go back to a previous state? Or what if you're giving it, for example, the wrong information about the inputs? Or what if you need to actually save the state for a moment? So it becomes less of a problem about like, can I generate the input in a dictionary, and more of a problem of, am I generating the right input? And someone asked me a question the other day about reproducibility, which traditionally was not used so much in the sense of like the actual inputs and outputs, but now it has me thinking in that respect if we're going to be running into issues in workflow reproducibility.
Yeah, that's a good point, and oddly, it's been a problem even in traditional workflows for a long time. It's something that some of the cloud solutions actually did a really good job with. I mean, we can argue about whether Hadoop was a good or a bad thing, but you look at like Spark and being able to actually do automated recovery of steps, and the vast majority of even traditional workflow tools just don't even try. It's an explosion. So that, I think, is a kind of a good point of a general issue maybe we could work on.
So your point there about recovering the steps, I always ask, like, okay, great, we've got this technology, and it's accelerating us in one area, but to what effect? Like so what? Like, how are we going to use it? How are we going to, if you have to go and publish an article that includes a methods section, how would you actually describe the methods that the agent is taking, and how would you stand and defend that is trustworthy solution to the scientific problem, or that you're following the proper method for it, right? And I think we're still discovering ways that we can do that, but there's promise to at least get the grunt work, you know, the rock fetches that you normally have to go and submit all the different jobs and tie up the inputs and outputs and all the stuff that is tedious. Maybe the agent takes care of that for you, but we still need a good way of tracking when it's the right approach, or it's the approach that you intended when you're trying to argue your case for the scientific discovery.
Yeah, and what about access and availability of models? So sure, you can, pay for tokens on a cloud, but the speed at which those models change and increment, by the time you publish your paper, maybe the model that you use is not going to be available. And so if you're at a lab, though, you're not even allowed to use those models. You have to use the on-premises models. And maybe they're a lot older. They're a few generations older because they had to be set up. Maybe tool calling isn't enabled, or maybe tool calling is enabled and it really doesn't work well. So there's all these additional kind of challenges that we have, at least when we're coming from academia, using the models, and that doesn't even get into like when we publish them, how the world's going to change.
All right, so I want to transition from workflow managers into resource managers, and I'm going to take an audience question. I think this is a great question personally. So both cloud and conventional HPC have their strengths and weaknesses. How much should an ideal resource manager of the future take from both?
What them both?
From cloud and HPC. So cloud and conventional HPC have their strengths and weaknesses. So how much should an ideal resource manager of the future take from both?
All right, well, I guess I'll at least start this one off, since I putatively lead at least an HPC resource manager. I think there are strengths and weaknesses of both. Things that have actually come up at different points in this. I think Vanessa brought up one of the points earlier, that one thing that tends to be missing in a lot of cloud environments is the option to request that something be run eventually, right? And be able to wait for resources to become available rather than getting a, nope, we can't get it for you after some unknown amount of time. On the HPC side, I think the main kind of almost inverse of this, in HPC, usually you're saying, I need 10 hours of such and such resources, get them for me and give me an answer when you can. In cloud, often you're saying, I want, however many instances, possibly scaling, possibly whatever, but I want them until the end of time, and I'll tell you when I'm done with them, which may be in 10 seconds or maybe 10 years from now. And there's nothing in there on either side that lets you mix in a meaningful fashion these kind of timed, I want it done, but I don't particularly care when, and services where I need it to start soon and I want it to run in perpetuity. And figuring out how to put those together, I think, is one of the kind of big issues. Now, the other one I think we really ought to try and take from cloud is offering more mechanisms for what to do if you need to scale what you're currently doing. You need to be able to expand or reduce resources. And in a similar vein, being able to deal with partial failures, maybe be able to request more resources come in because a node failed or things like that. There's a lot better support for that in my experience in more cloud stuff.
I think with HPC and cloud, I actually think there's a problem with me too. And this actually then reflects in how the services are used. So when I use cloud, I plan everything. I have spreadsheets, I know my total cost, I calculate the time of something to run, I plan a testing phase. I mean, I am so efficient in using things because there's a big penalty if I mess up, and I can't mess up. When I use HPC, I SSH in, I have infinite access to all these resources. I don't think about anything. I'm probably very wasteful. If I submit a job and it doesn't run, no problem, I'll run it again. And I feel like if I took that same very routine that I have with cloud, where I'm very efficient and I keep track of what I'm doing, my usage on HPC would get a lot better. So I think my overall sense, and I don't know if I'll articulate this well, is that there's also a cultural problem in the rules that we're used to, the environments that we're used to, and the decisions that we make as a result of that for how we use the resources. But then we come back and we kind of think about it and we reflect like, oh, this is a problem with HPC or this is a problem with cloud, and we never think about how can I change my behavior so that actually this environment, it has, for example, better utilization for everyone.
So even in the static footprint that you have on-prem, you can go and estimate the cost for that. And I was actually telling Connor yesterday that to go and estimate the cost for what he's doing in his PhD research, right? Like when you start to put dollars and cents to the work that you're doing, you start to realize the value that someone else is investing in you and the project that you're working on, and it really does change your view on all of this. That you're not going to be as free about or carefree about going and submitting a job that you know is going to fail, just so you can gather more debug logs. You'll put more hustle into debugging before you even do that attempt. So I encourage everybody to go out and come up with an assessment of what their costs are in static hardware, because you know what the budget was to buy the system. You know how many hours you're using in the CPUs. You can start to translate that into something that's more meaningful.
Yeah, that's something, putting my center hat on for a second, that we've discussed a lot, is how you can make it visible to people what that cost is, right? Because one of the major differences from cloud to us is that cost model to the user, right? If you have a direct cost to yourself, there's a very different reaction to that than when the cost is in batch priority, right? If it just means your next job will take a little bit longer to start, unless that impacts your job, it's not something that people have a tendency to worry as much about. We've done some studies on this, trying to figure out how to put back pressure on things for people to optimize their code, run more efficiently, do things like this. But it's a very kind of difficult thing for us to square, because there's often you're not actually getting money or something from a project. They have a number of CPU hours, right? So even if we present, like when a job completes, or send somebody an email saying you've used X dollars of compute, it doesn't hit quite the same way. Like I would actually love to find a way to do that if people have thoughts on that.
Let me just break for a second. We've got one more question from the audience. I think we probably have one more question after that.
So 2 quick points. These are more comments than questions. The first one is, some of the language that's being used is actually really interesting, because we're positioning like HPC versus cloud. And
No versus. HPC and cloud. I have made that point in talk. I apologize if we said that we were wrong.
I can appreciate the amendment, but a lot of that language is very visible here. It's conventional HPC versus cloud, and I think it really behooves this entire community to really start thinking about how do we bridge those two things.
Agree.
So that's the first thing. The second thing is, I think we're overcomplicating a lot of this, because a lot of these are solved problems. The whole serverless methodology is exactly the solution, right? Like, these are complex problems, but they're not complicated. So I think that I'd push back on a lot of some of the things that were said, but I understand that there's a lot of nuance here.
No. So it is very easy to look at this and say that they're solved problems. I've had people come up to me and say, oh, scheduling's a solved problem. Yeah, we've been doing it the same way for 20 years. Yeah, that doesn't mean we're doing it right. And yes, it's true. You can make a solution that will work quickly. A solution that will work well for any given use case is a completely different issue. And the serverless computing setup for HPC or for jobs that have locality requirements is hilariously awful. Like, many orders of magnitude worse than almost anything else. So, no.
Preach.
You know, we've talked about processing and computation, but what about storage?
Yeah.
You know, that's another, that's a valuable resource, right? How do we better, you know, better make use of that?
Yeah, that is absolutely true. And selection in storage, there's been some interesting work from some of my colleagues on that recently, is a very underserved problem, especially when generating data, right? Like, actually deciding where to put it so that you don't have to pay an awful amount to get it where you need it next is oddly underexplored.
I'm asking the question of somebody who needs to do that.
Yeah, storage is one of those things where we have a very different mindset for cloud and HPC. At least, I guess you may not, but for me, when I use cloud storage, I'm very specific. I try to keep things organized. My HPC directories are like a wasteland of forgotten files. Like, when I was at grad school, like, everything just accumulated, and I got the reminders from the sysadmins about deleting stuff. Did I delete it? Absolutely not, and I was wasteful. So that's another thing we could do better.
All right, let me interrupt one more time. We've got time for one more question.
All right, since we are talking about resources, I think we often tend to see this as technical resources only. Like, we've talked about storage and compute, but if I'm a scientist, I might not know better, and I might be wasteful because I just don't know better. Should I invest my time rather in getting better at just managing the resources that I need to compute X and Y that I need for my research, or is it fine to say it's not very efficient, but it works? Like, that's, I think, the scope of this question is as large as you want it to be. And it's easy to say, oh yeah, we need better scheduling and we need this and that to be more efficient. But I don't know if in the big picture of science and how we do science right now, that actually is that big of a difference.
I think in practice, with the way that things are with like the publishing cycle and the need to get work done by a particular time, scientists are kind of forced to, like, it just needs to work well enough to fit within these constraints. Now, does that mean that you couldn't take it to, for example, a research software engineer, if you remember the research software engineer movement, and have it be optimized and run better? You could, but is the incentive there for that? And actually, this is another difference, sorry for the versus thing again, this is the difference between cloud and HPC. It's with respect to the level of system support. In HPC, you have your team of system HPC admins that are maintaining the entire software stack for you. They have embedded all of the expertise in the network working the best that it possibly can into the system, as opposed to when you go on cloud, you may be forced to set that up yourself, and maybe you can't.
Yeah, and this is something I think a lot of different places, us included, have been trying to solve at different levels. There's what your scientist knows, and if you can take that expertise and set up tools that they need so that they can get more out of it, then we benefit significantly. But if it's a bespoke tool, then the solutions have to be different. And that's always going to be something we have to deal with, because people are trying to solve novel problems. That means they need to build novel tools to solve them. And at least some of what we're trying to do is make it so that instead of having to know all the details of the system, the more you can describe the way that your software needs to run, hopefully we can help make better decisions in an automated manner, right? It's yet to be seen just how far we can get down that path, right? If you insist on writing all of your software in unoptimized Python, well, there's a limit there. But
Yeah, but that's one area where we are seeing some of the work on agents coming. It's bearing fruit. That you would have some red teaming, or you'd have agents that are observing your inputs and giving you suggestions to guide that. And they're remarkably valuable today, where you can input like a Fortran code, and it'll say, well, hey, I found you're using arrays of structures. Switch to structures of arrays for better memory access patterns. I mean, the detail that a scientist usually won't think about, right? So I think there's a lot of promise in that, but again, early days, so we'll see how it continues to bear fruit.
Yeah, and that's something we as computational scientists need to meet other scientists kind of halfway, and make sure they understand where we're coming from, or understand where they're coming from as well. How do they think? What's their unit of computation? How do they think, and how can we better provide resources for them?
All right, so I know we're over time at this point. Looks like we're actually in break, but we can stay for one more question if people like, or if we're going to get kicked out, I'm not sure. No? All right, so let's thank the panelists. Thank you very much.